Have you ever really stopped and thought about what's happening inside the device you're watching this on right now? We use computers every single day, but how they actually work, it can feel like pure magic. Well, today, we're going to pull back that curtain. We're going to demystify all of it right from the very beginning. So let's just dive right in. How does a machine, a lump of silicone and metal, go from being an inert object to something that can calculate and communicate and even create? The answer is actually surprisingly simple. And it all starts with a concept you already know inside and out. That's it. Seriously, a switch. Think about a light switch on your wall. It can be on or it can be off. There's no in between, right? No dimmer, no gray area. It's one or the other. This simple two-state idea is the absolute bedrock of everything a computer does. Now, in the world of computing, we call this tiny piece of on or off information a bit, and we just give those states a number. On becomes a 1, and off becomes a 0. This is it. This is the only language a computer actually speaks. Everything you see, everything you hear, your photos, your music, this video, it's all just an unbelievably complex pattern of ones and zeros. So if the switch is the key to everything, then you could say the entire history of computing has really just been one big quest to build a better, faster, and smaller switch. It really started back in the 1940s with these things called mechanical relays. These are actual physical switches. You could hear them clicking open and shut. Then, in the 50s, we got vacuum tubes. They were faster, sure, but they were huge, hot, and broke all the time. But then in the 60s, came the real game changer, the transistor. And here's why that was such a huge leap. Mechanical things, by definition, have moving parts. Moving parts are slow, they wear out, they break. But electronic switches, like transistors, they have no moving parts at all. They control the flow of electricity silently, reliably, and at speeds that are just almost instantaneous. Getting rid of the moving parts was the breakthrough. The transistor is really the hero of our story today. Because it was made out of silicon, it could be made microscopically small. It was unbelievably fast, used barely any power, and it was cheap to make millions, even billions of them. This one tiny device became the fundamental building block for all modern electronics. Okay, so we've got our perfect little switch. But one switch by itself is, well, it's pretty boring. How do you go from a single on-off button to something that can actually make decisions? Well, this is where things get really cool. This is where we start building with logic. When we combine a few transistors in a specific way, we create something called a logic gate. The best way to think about these is as tiny little decision makers. They take in one or more bits as their input, so some ones and zeros, and based on a very simple rule, they produce a single bit as their output, a single 1 or 0. Okay, so let's look at a basic one. This is the AND gate. Imagine you have a lamp that needs 2 switches to be on for it to work. The light only turns on if switch A and switch B are both flipped to on. It's the exact same idea here. The output is only a 1 when both input A and input B are 1. Any other combination and you get a 0. Then we have the OR gate. Let's go back to our lamp, but this time the switches are wired differently. The light will turn on if switch A or switch B is on. Doesn't matter which one, or even if both are on. This gate works the same way. As long as at least one of the inputs is a 1, the output is a 1. And finally, this is a really important one, the XOR gate. That stands for exclusive OR. It has a special twist. It only gives you a 1 if the inputs are different from each other. So if one is 0 and the other is 1, you get a 1. But if the inputs are the same, both zeros or both ones, it gives you a 0. And this simple little rule, as you're about to see, is the key to making a computer do math. All right, so we have these tiny decision makers, AND, OR, XOR. But how in the world do we get from there to, say, a calculator? This right here is the aha moment. This is where we combine these simple little gates to do something genuinely useful. First, a super quick refresher on how computers count. We use a base 10 system with 10 digits. Computers only have 2 digits, 0 and 1. So they use base 2, or binary. Each place value isn't ones, tens, hundreds. It's ones, twos, fours, eights, and so on. A 1 means you turn that value on. A 0 means you leave it off. So if you want the number 13, you just turn on the 8, the 4, and the 1. In binary, that's written 1, 1, 0, 1. So let's try adding 12 and 9 in binary. 12 is 1100, 9 is 1001. We just add them up, column by column, from right to left. But wait, when we get to a column where we have to add 1 plus 1, we get 2, which isn't a digit in binary. So what do? We do the same thing you learned in first grade. You write down a 0 and you carry the 1. When you do all that, you get the answer 10101, which, if you add it up, is 21. It works. So, how do we build a circuit that can actually do that? Well, to create a circuit that can add two 4-bit numbers together, just like our 12 plus 9 example, you'd need to arrange a combination of AND, OR, and XOR gates built from a grand total of 64 transistors. And that is the magic moment. The first time you see those simple little gates wired up in just the right way correctly perform a task, like addition, it's just a feeling of pure discovery. You've taken a simple switch and you've taught it how to do math. It's an achievement that, well, as the engineer who first did it said, is definitely deserving of 2 thumbs up. Okay, so we've built a tiny little calculator that can add 2 numbers. That's amazing. Now, let's zoom way out and see how we get from that to the absolute powerhouse brain of a modern computer, the microprocessor. The engine that drove this incredible journey is something called Moore's Law. It's this observation that for over 50 years, engineers have consistently found clever ways to shrink transistors and pack more and more of them onto a single chip. This relentless exponential growth is why the phone in your pocket is literally millions of times more powerful than the giant room-sized computers from the past. So what does that kind of scale look like today? Well, a modern processor, like the one in a desktop computer, can perform around 400 billion operations, like that simple addition we just did, every single second. I mean, that is a number so astronomical, it's almost impossible to wrap your head around. And really, this is the fundamental takeaway. A computer's thinking. It isn't some mysterious, magical process. It is just very, very simple logic, performed by billions of microscopic switches firing billions of times per second. That's the secret sauce. Simple logic plus unbelievable scale and speed. There's this beautiful analogy that just frames this whole thing perfectly. Back in the 70s, a study was done on the efficiency of locomotion for different species. And humans, we were pretty mediocre, somewhere in the middle of the pack. But a human on a bicycle, they were twice as efficient as a condor, the most efficient creature on the planet. A computer isn't a new kind of mind. It's a tool. It's a bicycle for the mind that amplifies our own inherent intelligence. We've just traced the path from a single, simple switch to a device that can do 400 billion things a second. And those switches, those transistors, are only going to get smaller and faster and more numerous. So the real question this leaves us with is, what incredible new things will we build with the next generation of these powerful tools? What new trails will we blaze?